Thanks.
We're ready to go.
Go.
Okay. So, I want to go through the various formal models that we've produced of the FMI standard. It'll be a very quick overview, I should say. Last time I did this, it took 2 hours, and I've only got 10 minutes. So it'll be brief. So the first question has got to be, why do we want to create formal models? And what this comes down to is, if FMI is going to work, then we need lots of independent groups to be able to produce FMUs and tools to integrate FMUs and have them all work together seamlessly without strange problems cropping up when you mix them. And to do that, everyone has to follow the same standard. And for that to work, the standard really needs to be clear and unambiguous. But because of the way the FMI standard is written, that's to say, mostly natural language and tables and diagrams, it's semi-formal at best. It's open to some interpretation, and there are definitely omissions. So the idea of a formal spec is that we clarify those ambiguities, fill in the omissions, and then everyone hopefully is on a much sounder footing, and it increases the likelihood of everyone being able to work together seamlessly. But if you think about that for a minute, how on earth can we create a formal model if the thing that we're trying to model, the standard, is informal, if it's ambiguous in some regard? So this is true. So what we're really doing is providing a precise interpretation of the standard, which may not be correct. We then take that interpretation and compare it, hopefully automatically, and I'll show you that later, compare it to what other people have interpreted through their manifestation in their FMUs and their tools. And where there are differences, we say, we think it's like this, you think it's like that, which is it? And hopefully, if we can clarify those points, we can then either improve the model or correct the FMUs. And so everyone moves towards a more precise interpretation of the standard. So that's what we're trying to do, to formally interpret the standard and then use that to improve the quality of everyone's FMUs. So how are we going about it? Well, we've written various formal models in the VDMSL dialect. VDM's a formalism that we have a lot of expertise in the group, and I think you've seen some examples of VDM earlier in the webinar. There are basically 3 classes of model. The first one, and that's the one I'm going to show you today, is called the static semantic model. And this just covers the rules that are to do with the configuration of an FMU. So this is the XML file and the settings and the variables, how you declare variables, what's legal, and so on. The second class of model are called dynamic semantics models, which I won't go into today, but this describes the behavior of an FMU in abstract terms. So what should the FMU do in general when the various API functions are called, and what should it return, and how should the state of the system change as a result, if at all. And the third class, which is outside the scope of the FMI standard, but it's important, is to model the behavior of collections of FMUs. So this is to help tools that do the master algorithm to coordinate simulations. And this is to do with the connection of inputs to outputs, the definition of algebraic loops, the initialization process, and how you decide what the initial state of the whole system is. We're working on both FMI2 and FMI3. FMI2 is much more mature, and we're up to version 2.01 on that, and that's fairly stable now. FMI3, by comparison, is changing by the day. And I'm desperately trying to keep the model up to date and the schema up to date and so on. So that's a work in progress. But we're tracking both versions of the standard. So talking just about the static semantic model, this is really from a formal point of view, just one large Boolean function, one predicate that says, is this configuration valid? Internally, it's structured as a set of functions called isValid, and then the name of each XML type. So the top level function is valid FMI model description, because that's the top level XSD type for the configuration. Each function implements the rules regarding its immediate children and the interactions between them, and then it calls down to inner functions for each subtype. So FMI model description will call down to isValid scalar variable, because that's a very important component of the model. And there are other components. And then scalar variable will go into isValid real and integer and Boolean and so on. So that's all pretty straightforward. Yeah, although the devil is in the detail. But as it stands, if you just did that, if you called isValid model description, FMI model description, it would just give you true or false, which, whilst interesting, isn't very useful. True is useful, I suppose, but false, you really want to know what's wrong. So as well as just being a Boolean function, the VDM logic is annotated. So at the bottom there, we have an example. The logic on the last line is just saying, if you have a maximum and a minimum defined, then the maximum has to be greater than the minimum. And that looks like part of isValid real or something, or one of the integer types. The annotation above it means if this subclause fails, so this can be a sub clause, an arbitrary part of the evaluation, then print out this error message, or do something with it. At the moment, it just prints them out. The 223 is the section number of the standard, which tells you that the min and the max have to be related as they are. And the message should hopefully give you a clue. The example there doesn't give a line number, but in the real thing, it would give a line number in the XML where the fault had occurred, or the variable name, so that you could find out what was wrong. So all of the annotations get executed across the function, and you get a list of error messages as well as the value false to say that your configuration isn't perfect. So that's good, but as it stands, the only way you could use that is to get a formal VDM IDE like Overture, and you would have to understand how to extract your configuration from an FMU and how to turn it into VDM so that the VDM model can understand it. And there's lots and lots of little details before you could get anywhere near calling the isValid model description. So to make it useful, these, I think there are 6 steps there, have all been wrapped up into a script so that people can just easily use the model, the formal model, to check their FMUs. And well, I really said what you do there. You extract the XML. The XML is checked against the XSDs. Then if that passes, the XML is generated. Oh, sorry, VDM is generated from the XML so that the model can understand it. It puts the whole lot together with the definition of the formal model and executes the valid function, and then the on-fail annotations print out anything that they find that's wrong. And that's all wrapped up into a shell script. There's also a pure Java version for people on Windows. And the result is similar to a tool that is provided by the FMI consortium called FMU Check. But we think that the VDM model is much more precise about the checks, and I'll show you why I think that later on. Okay, so that's its usage, but I'd like to try and give a demo. So I think you can just, can you now see the black screen?
Yes.
Okay, thank you. So in this directory, I've got 1, 2, 3, 4 FMUs, or 3 FMUs and 1 pure XML file. So if I VDM check 2, there's VDM check 3 for version 3. and just put in the bounce. That's all. That's the minimum invocation. Okay, so it's found some problems, or a problem at line 63. It's reported it in 2 different ways. And the last two messages are really saying vmin is wrong, and then the scalar variables are wrong. So it's sort of, as you come out of the nesting of the functions, you get these sort of summary messages. The others are pretty similar. Although they're different error messages. This one's to do with aliases. The rules around aliasing of variables in the FMI standard are tricky to get your mind around, and it's not unusual to find tools have broken the rules. There are various strange rules in section 227 that you need to follow. I think the integrated signal is clean. Yes, so that's no errors found. That one's perfectly okay. And the model description, I beg your pardon, has got some errors to do with start values and min-maxes and other things. I see it talks about effective variables there. This is saying these variables have inherited some values from a data type rather than just having everything defined in line. So this is one aspect of the standard that's not very well explained, and we've interpreted the effective values that you get through data type inheritance, really. Also some interesting ones at the end there. The derivatives have been declared, but you haven't got any derivative variables. And the initial unknowns have to include various things under certain circumstances, and those have been missed out.
Be aware of time. You were kind of over time, so don't go to all the details.
Okay. You mean hurry up, don't you?
Yes.
Hurry up. Okay. So quickly, we've got a tool. We've run it on all the FMU version 2s that we could find in what's called the crosscheck repository. There are about 700 of them, and compared the results with FMU check, which is a standard tool. So we reckon that only 42% of them have no problems. Let's say 58% of them are broken in some way or other. You'll see FMU check says 77% are okay, but it's got zeros for a lot of those categories of errors. The only one where we agree perfectly is the variable names. And the reason we agree perfectly is that part of the standard uses a formal language. It uses an EBNF grammar. And of course, when you use a formal language, everybody knows what it means, and we agree perfectly on what the errors are. So in future, we're going to keep trying to establish the intended semantics of the FMI, mainly FMI 3, and raise issues with the FMI org to try and get those resolved. As FMI 3 FMUs appear, we'll check those. It's, as you saw, it's not very slow, but we can make it more efficient with Overture code generation in principle, and that might be useful for the tools that once we incorporate this, such as Maestro, the last line there, we'll be building some of this formal validation into our own tools so that we can see anything's wrong before we start trying to run a simulation. And that's it, Peter.
Thanks, Nick. So in due of time, I suggested you'll just type in questions you may have for Nick, and otherwise Christian should try to share his screen.
Okay. Do I need to unshare? I'll unshare.
Yeah.
Can everyone hear me?